Good afternoon, everyone. I hope you are doing all right. So, last class we talked about reflection, refraction, and then we talked about reflections in mirrors, plane mirror, concave mirror, convex mirror. We talked about mirror formula. We talked about how to draw a ray diagram to locate the position of image, okay, and also how to locate the position of image using formula. So today, basically, it's a kind of continuation, but today going to be on refraction. So, so here you see this says total internal reflection on the heading, but it is also related to refraction. So total internal reflection is a special case for the refraction. So in this video, hopefully it works. You see there is a rays of light and there is a piece of glass or something like that, plastic or glass, sitting there. There are these different angles shown. So in this video, they're going to shine light that passes through this uh, plastic or glass piece and then gets out to the air. Okay, so this is a boundary. So now let's see how the light behaves. So we learn about reflection and refraction, right? So how this total internal reflection arises. So that's what it talks about. Hopefully this works. And there is no sound in this video. So one thing you notice here is that when ray of light passes straight perpendicular to the surface, it gets out, perpendicular. So that means when angle of incidence is 0, in that case angle of reflection and refraction, they are also 0. Okay, so the fun begins when you start making the angle, okay, not the 0 degree angle of incidence but larger than that, and that's what you see there, marked here. So this light gonna be shining from this different direction, and notice how this one gets out from this glass. So pay attention to this part. Okay, so this is an example of refraction. So it's getting out from this. So it's getting out from this glass block. Yeah, it's written glass block, so I believe that's a glass. And it gets out to the air. So in this case, light is, the normal is shown here. So the angle of incidence, if you pay attention here, is smaller than angle of refraction because the light is getting out on the air, which has smaller refractive index than the glass. So last class when we talked about, the situation was something like this. Light was coming in from the air. So think about reverse, okay? It's coming from the air and entering to the glass. So if you think that way, then what happens? The angle of incidence here is larger than angle of refraction. So it's kind of, these are reversible phenomena. If I were to put a plane mirror here and reflect this light perpendicularly, that means plane of the mirror is 90 degree with the ray, or the angle of incidence is 0. In that case, this ray of light gonna just retrace and follow this path, okay? So as the angle of incidence increases, angle of refraction also increases, okay? But something happens at a particular angle of incidence. So now around 40 degree here, you see there is refracted ray, but there is also reflected ray. So now it's reflecting back to the glass following the law of reflection. So in that case, angle of incidence is going to be this. Hopefully you can see the mouse here. I'm not trying to write here, but let's say this is angle of incidence and this is angle of reflection, and reflected light is here, is pent, but it's going to be better. And this is angle of refraction. Let's say theta r, angle of refraction versus angle of reflection. So angle of reflection, see these angles, they are same, but this end, this one here is larger. Now at a particular angle around this 40, what happens is the angle of refraction becomes 90 degree. Let's pay attention to that. See, now more and more light is reflecting, and at that angle slightly more than 40, oops, wrong place, I clicked on the wrong place. So around here, you see, the light is just, this refracted ray is making 90 degree. And a lot of light is coming reflected. So the angle at which this angle of refraction becomes 90 degree is a, critical value, we say. So this angle of incidence is also called critical angle. So in this case, we see it is slightly more than 40 degree. So this is glass. Glass has refractive index around 1.5. Okay. So if we were to use that refractive index of glass in air, we should be able to calculate that. So now, once the angle becomes slightly more than that critical angle, all light is just getting reflected. So that's what the total internal reflection is. Okay. So there is a question here on the Zoom that came as a direct message. Let's see if I make that for everyone. Yeah, I think you can message to everyone. So why does refraction happens at a particular angle? So what happens is the refraction happens because the light slows down when it moves from one medium to another medium. Or let's say it goes faster. When it goes from, let's say, glass to air, it's going faster. And then when it goes from air to glass, what happens? It's going slower. So in that case, what happens is it kind of gets refracted, it bends a little bit, and it is not just for light, it is for us as well, actually. Okay. So for example, if you enter a boundary of sand in the parking lot at an angle, not directly straight, so if you are walking, it's hard to tell, but if you are riding bicycle, and if you enter at an angle, what happens is you notice the bicycle slows down, and then your kind of handle, if you are not handling correctly, it kind of goes bends a little bit. So when object slows down while going from one medium to another medium, it has a tendency of changing direction at that point. Okay, so basically that's an observation. Okay, that's a good question. So now, next slide, I have actually the screen capture of these slides. So you see there is this refraction going on. Oops. There is this refraction going on, and this is the theta 90 degree situation, not 19, but 90 degree situation here, which is angle of refraction. So this angle is called critical angle. and over here it's reflecting totally. So that's why it's called total internal reflection. So this angle here and that angle is equal according to laws of reflection, and we can measure and verify that. Okay. So I have drawn those sketches over here, and I'm also writing equation. So this is Snell's law we talked about last class. So while using this equation, what you see is there is product of n and sine theta. So that one repeats. For one side, there is one kind of subscript, and for another side, there is another set of subscript. So this angle has to be on the same side the refractive index is. So in this drawing, I'm assuming that this refractive index N1 is for this material that is shown by shaded area over there. You can think of that as a, let's say, a glass. Okay. So N1 is there, and theta 1 is the angle made by the light on that side, angle made by the light with the normal at that side. Okay, so that's how you need to keep in mind. So once you remember that this product is same, then other than that you don't have to. Sometimes you may see there is formula written for this critical angle, but this comes from just that. Okay, so basically this is the formula. This is just one step back. So when we simplify this, we get the critical angle. So that's how you want to learn to get the critical angle starting from this equation. That's the basic. Okay. So when this is angle on this side, that means it was theta 2, right? So when theta 2 becomes 90 degree, then this theta 1 is called a particular value because it's showing some interesting behavior, and that is called critical angle. And once we, so now let's, like sine 90 is 1. So that means sine theta c, oh, I just copied that for some reason. Sine theta c is n2 over n1, okay? And from here we can solve for theta c, okay? So for example, that's going to be arc sine or inverse sine n2 over n1. So in this case, the n2 is the refractive index where the angle was 90 degree. So in this case, if we assume this is air, not air, that means this refractive index going to be 1. And if this is glass, then that is refractive index is 1.5. So if you have calculator handy, go ahead, do the calculation. It should come out slightly more than 40. Okay. So now once this angle becomes, like let's say, oh, it's supposed to be larger than that. My drawing, I kind of made bit smaller, huh? So once this theta 1 becomes larger than theta c, so theta 1 has to be larger than theta c. When that happens, what happens? We get these two angles equal. So in this case, theta 1 has to be larger than theta critical. Okay. And that's the total internal reflection. So there are a lot of use. We make use of it in our daily life. So for example, the shiny diamond, you see, basically it's shining so much like that because of the total internal reflection. I think I wrote that one over here. Okay. Light reflects off the internal facets of diamond multiple times before exiting, and because of that, it appears bright inside when you look from a particular direction. This image I grabbed from somewhere. It looks like this is just the drawing rather than like actual photograph of diamond, shining diamond. So here is a question, for example. What is the critical angle for a diamond if refractive index is 2.42? So refractive index of diamond, so that means diamond is sitting on air. So one side gonna be air, another side is diamond, right? So now if we say diamond is side 1, then we can say, okay, refractive index of diamond is N1 and refractive index of air is 1. Okay, so what we can do is we can write the equation, let's say using, so in this case refractive index 1 is given, which is 2.42, and refractive index doesn't have unit. Remember, refractive index is ratio of speed of light in vacuum divided by speed of light in medium. So vacuum and air, the speed of light is about same. So we can treat air as a vacuum for the speed of light. So that is on the diamond side, I am saying N1, and the air side, I am saying that is 1. And we are given that refractive index, and we are asked to calculate what is the critical angle. So critical angle happens when angle on this side is 90 degree. So let's say, since we are saying I'm giving n two subscript there, so let's say theta 2 is 90 degree. So or we can say, okay, theta 1 is theta c when theta 2 is 90 degree. And to say theta 1 and theta 2, you have to actually mark which side you are saying 1 and which side you are saying 2. If you not the subscript here, which medium we're talking about, without that, the equation may not make sense. So now we are trying to solve for critical angle, and it's happening on N1 side. So I'm writing N1 sine theta 1 is equal to N2 sine theta 2, just like we did in the last slide. And N1 sine theta c. So when is theta c? When is theta 1 theta c? Whenever theta 2 is 90 degree. So using that, we can write something like that. And this is 1. So that gives us sine theta c as n2 over n1. And n2 is 1. I like numbers 1 and zeros. So theta c is inverse sine of n2 is 1 and n1 is 2.42. Okay, so that should give us the answer. I haven't done calculation. Can you do the calculation and type that on the Zoom, folks? So it looks like I have a calculator here. So how do I do this calculation? 1 divided by 2.42. Okay, so that's that. And then I want, oh, looks like this one wants the sign first typed first, looks like. Oh, that we need second functions, and that is inverse sine we see here. And when we do that, we get this 24.4 as the critical angle. So for the glass, it was around 42. Now for this one, it is 24.41. This is a 3-sig figure, right? So we can write 24.4 degree. Okay, so that's that. So just like I was saying, these days they say, okay, we provide you data, internet data with the optical fibers. So what is it then? So basically what they do is they make, you know, bundle of quite a few wire, but in each wire there is what's called cladding from a material, so that when data enters, let's say from this side, what happens, it is always totally internally reflected so that the data doesn't get out from the wire. And because of that property, there is no loss of data, and you can transmit large, data at larger or faster rate. And the endoscope they put inside your body has a light in the tip, so that inside the body, of course, we don't have light, so we cannot see it. But once we insert this tube with the light, what happens? It lights up our body organ, and then the light is totally internally reflected here, and then you can see it from there. Okay, and some of your car might have this rain sensing wiper. Whenever there is a sprinkle on your windshield, it starts, swiping on its own, wiping on its own. So that is also example of that. So for that, there is a light over there, and there is this coating that makes it go total internal reflection. Okay, and prism is an optical device. We'll talk about more optical devices next class, but it has this thing called prism. So prism is cut and designed such a way that light, you see here, so light is entering here. So now rather than getting out there refracting, is totally internally reflecting at that surface over there in that cut. Okay, so that's like a normal over there, and there is another normal over there, there is another normal. So basically what it does is it helps change the direction of light without losing the light, and getting all possible light is, you know, that's the goal, because that's what makes the image brighter. Okay, otherwise image is going to look dim if we lose light. So that's how the prism in binocular is doing this total internal reflection. Okay, so sometimes we see this funny looking, let's say situation. In this case, this is picture, but if you put something in the water, if you put, let's say you take a glass of water and you put a pencil over there in that glass, and then what happens? You see as if the pencil is broken at the inner face, or it can be spoon. It doesn't have to be, the pencil. So why does that happen? It is because of the refraction. Okay, it is because of the refraction of light. So what happens? The light coming from here, let's say this point is the original point, right? So original rod is here. So once light starts going and reaches to the boundary of the water, what happens? They refract away by making larger angle. So they are not just coming straight. When you are looking from this side, what happens? You are seeing this light there bent. And for our brain, light travels always in a straight line, so it appears as if it's coming from this point. And all the light that's getting out from each and every point you see over here, that's what they are doing, okay? They are bending away from the normal, and that's why they look like that. So this is not actual rod, rather it is the image of the rod that appears little higher than it is actually. So it appears in different, place. So if you are, so usually some people might be, enjoy, they may enjoy the ice fishing. So they make a hole over there on the ice and there is water down there and you sit and watch from here by putting some sort of decoy here. And when fish comes, what happens? Unless you look straight down where the fish is, if you are looking from the side, then fish might be here, but it appears over there. Okay, so that's what happens. And there is this phenomenon called mirage because of the, we can explain mirage phenomenon by using this refraction. So what happens? We have air, and air comes in different layers, and this different layer gradually either getting colder when it goes higher or getting warmer. It depends on situation. So for example, if it is hot summer day like what you see in this case, what happens? Air that is near the earth surface that are hotter than the air that is bit higher. So for each and every layer, temperature is getting a bit cooler and cooler, higher you go. So because of that, what happens is the density of air is slightly different. So because of that, there is gradual bending. So it's not, one phenomenon like when it enters from air to glass. Rather, it is happening gradually over these different layer of different temperature air. And then slowly what happens is it basically turns around, and when you are looking from there, it looks like that light, although it's coming from there, it looks like it's coming from there. And then even when there is no water or mirror over here, what happens? It seems like there is image. So here there is no water, but this is just the image of sky over here, over here. So that's what happening there, okay? You may have noticed it looks like, okay, road is wet while driving on hot summer day, but once you are there, it is not there. Have you ever noticed something like this? If you have, type yes in the chat. Let's see how many of you have paid attention during summer. Okay, so some of you said yes, other maybe trying to write it, or other, who cares? I already seen it. If you haven't, next time when it is, like 80 or 90 and you are driving on the road, pay attention and you'll see something like this. Okay, so that is when air gets cooler and cooler when you go higher, or gets warmer and warmer when you comes down there. But opposite may happen on cold day rather than hot day. Okay, so in that case, what happens? Rather than light starting from here and bending something like that, it may bend downward. And because of that, it seems like it's coming from up there, and it seems, hey, the ship is up there in the air. So this is of course the sketch, but this is actual image or the photograph. You see, it seems like this thing is floating on the air, not on the water. that is the region. Okay, so when it is really cold water over here, and up there sun is shining, but water is still kind of freezing cold. In that case, you may observe something like this. So usual mirage, that's what we call mirage, and this is called superior mirage. But since this is superior, this may also be referred as a inferior mirage. Okay. Oop, a lot of time when talking, so I am now letting you respond to this. 30 more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. So we got mostly C, and that is correct response. Okay. So it's not sudden change, but gradual change in temperature of the air layers. So we learned that when light goes from rare medium like air to denser medium or medium with higher refractive index like glass, we learned that it bends towards the normal. And when it comes from glass to the air, it bends away from the normal. So keeping that in mind, what do you think which sketch here is the better sketch showing the situation? So light enters from here on the air and then goes to this glass piece where this dashed line shows the normal, and then there is air on this side, air in this side. Of course, the glass prism is sitting on the air. 30 more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. So mostly A. Hmm. is a correct answer. So let's see here what's going to happen. Let's look at this boundary here. So there is normal. So this is angle of incidence. So it's going from air to glass. So it basically, if it wasn't bending, it would go like that, but it's going to bend a little bit in that direction, right? And then inside the glass, it travels a straight line. And if we think this as a normal, and then what happens? It makes larger angle with the normal. So this A is not making larger angle with the normal, rather C is making larger angle. Okay, so C is correct answer in this case. So let me mark that. So another thing here I like to point out is that, see this prism, they have like, on one, so this is one face of prism, this is another face of prism, and this is bottom of the prism, let's say, sitting there. And usually it's symmetric, so you can flip them over and put in any surface. But when it's sitting something like that, when we are drawing, so what happens? It seems like when light enters, it kind of bends towards the base, what we call base of the prism, rather than this peak of the prism. Okay, it bends towards the base of the prism. So that basically helps us to design what we call lens. Okay, so here is the drawing that shows you that, okay, so it's happening something like that, happening something like that. And these different color of light, they have different refractive indices, and because of that they bend at different angle, slightly different angle. So that's why white light spreads into this color. So I have slides about diffraction at the end as well, just in case if we don't make. And for example, if the prism wasn't there, this light would have gone just like that, right? But it's coming out something like this. So this angle here, original path versus now the new path, is called angle of deviation because of the prism. So now we can think of a lens is basically stacking of these prism, let's say. Okay, so there is one prism here. So this is upright prism, let's say. This is down, facing down prism. When their base are lined up like this, right, sitting something like that, it makes this shape. So any light passing this way goes towards the base of the prism. And for this prism, base is over here, so that's why it's bending something like that. So we can think of this as like pieces of prism, something like that. So what happens, this line over here is passing normal to this surface or making angle 0 degree. So that's why this line does not bend. So if light ray passes something like that, it won't bend, but any other, they're going to bend towards this line because I'm drawing this line right at the middle of this kind of structure. So that's why light from the top bends down and light from the bottom bends up towards that, what we call optical axis or principal axis of the lens. And all of those gonna focus at a point or come and meet at a point. That point is called focus, and this distance between, let's say, center of the lens and the focal point is called focal length, and we define something like that. Okay, so I'm showing those things for two kinds of lens, convex versus concave lens. Okay, so the lens is, you can pass light from this side and light comes from this side. Light going from this side comes out that, so it is, in that sense, is different from mirror. Okay, mirror, what happens, light has to reflect, right? Light has to reflect, because there is this coating that doesn't allow light to pass through. But in case of lenses, light can incident from one side, either one of those sides. So because of that, we have these focal points. Okay. So we saw last time mirror also has a focal point, and think about mirror as the small portion of that sphere. Yes, mine doesn't look like a sphere, it looks more like a potato. Okay, some weird potato, but you got the idea. So you can think of this has this one curvature, something like this. So think about this. This is that, and then there is another one. So when you look this piece here, so that is this lens over there. Okay. So this is called convex based on its shape. If it is bulging out, means convex, right? And if it is bulging in, then that is uh, concave. But both of them have a focal point on both sides, and we can have focal length. If their curvature is symmetric, then their focal point gonna be same. So there are different kind of lenses. There may be symmetric versus non-symmetric, but for this class, we're gonna be just looking at the symmetric ones, okay? And focal length for concave mirror is counted as a positive, sorry, not positive, negative for the concave, and for this it is called convex because this one converges light to the focus. So for example, if we put parallel rays just like we did for the mirror it went same direction and kind of went something like this. But for the lens it can pass through, but in that process it's supposed to go from here. Okay, so that's what happens. But in this case, if light is coming something like this, what happens? See, because of this, this curve, something like this out inward curve, what happens is it passes and then kind of goes such a way that it looks like as if it's coming from here. So this ray of light is not actually arriving there. It appears to arrive. So because of that, this we call, you know, partial focal point, and the focal length is called, we take that negative. So just like mirror formula, lens formula is also, same formula. So only thing is that we have to be careful using the sign of the P, Q, and F. Okay. So once we figure out how to, write the signs correctly, and then it's just a matter of solving that equation, just like we did for mirror. And of course, we're going to look example here as well. So for the concave lens or diverging, that's why this lens is also called diverging lens. Concave or diverging lens, if this distance, for example, is 10 centimeter, then we say, okay, F is negative 10 centimeter. So that's how we use. And for this, if this distance is, let's say, 10 centimeter, and then we say, okay, F is positive 10 centimeter. So here, what we are assuming is this lens is really thin, okay? So if it is thicker, bit thicker, then this formula may not work very well. But as long as it is thin, it works, and that's what we are assuming, and we're going to be using this formula. So just like mirror, you can use this formula for the lens as well. And here is a question for you. Okay. So this is converging or convex lens. That means focal length is positive. So with that, I'll let you work on this. So if you forgot your formula, you can write something like that. Does not have to be in a particular order. Oh, looks like there is formula here. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. Okay, we have varieties, but a bit more for the B. So I don't know the answer. So how do we do it? Object is at 2f distance, so object distance is denoted by P. So it is given in terms of focal length. So for example, if focal length is 10 centimeter, then object is at 2 times, that means at 20 centimeter. So that's what that means. Use the lens formula to calculate the image distance. So Q is what? So that means 1 over 2f, so using this formula, plus 1 over q is 1 over f. So 1 over q is 1 over f minus 1 over 2f. Okay, so now let's see, I know how to subtract this. So 2f over 2f minus 1 over 2f gives me 2f, and that is f. Oh, hold on, this is not supposed to be 2f, just 2 over there. Okay, and so this, oh, so that's why the f does not cancel. So this is 1 over 2f for 1 over q, but we need q, so we need to invert it. So we get 2f. So yes, B is correct answer. So when object is at 2 times the focal length, at a distance 2 times the focal length, the image is also exactly formed right there. That's what it is showing. And thanks to, again, this Learn and Have Fun YouTube channel, they have made this video. So they mark these different, so this lens is over here, okay? So this is convex lens. And focal points on one side, they are writing negative, on the side positive, but it does not have to be that way, okay? So just, I would just say, okay, focal length is 10 centimeter, okay? So, oh, focal length is 20 centimeter, not 10 centimeter, okay? And double of focal length is 40 centimeter. So now there is double of focal length on the other side. So notice how when they put object over there, they get image over there. So they're going to be casting image on the screen. So pay attention. So let's play. Infinity means very far. So you see tiny, tiny image. So now they are shining with the laser, and see these laser lights are parallel, means as if they are coming from the very far. Okay. So in that case, these light meet right at this point. So that is the focal point. Okay. So that is experimental proof, let's say. So image is inverted image, and looks like it is a bit smaller. So image, when object is bit farther than 2f, image is formed between 2f and the f, somewhere between, not exactly in between, it depends on where the object is. So that's where these light meet. So object is exactly at 2f and image is also exactly at 2f. See that? They have several other related videos. If you are interested, you can go to their channel and watch that when you have time. So once the object comes closer, the image is getting farther. When object was very far, the image was at focus. And then once object started coming, image started moving farther and farther. Okay. So when object was at infinity, image was at focus. Now when object is at focus, the image becomes, at infinity. When it is close to focus, I should say. So anyway, it's kind of getting long. So now you should be able to draw a ray diagram to locate image. Okay, so that's what you should be learning. And another one is that use the formula to locate the position of image. Or if object and image distances are given, calculate focal length of the lens and so on. Okay, so to draw or tracing the image, also called, these are also called ray diagrams. I am choosing same three principal rays, okay, just like we did for the mirror. But for the mirror, what happens? They reflect on the same side, but for the lens, what happens? They gets refracted, they pass and go to the other side. So that's what you see. The one that comes parallel to the axis. So which three rays we always use for the drawing principle, like let's say drawing the ray diagram to look at the image. One, the ray that is parallel, another one going to the center of the lens, another one that passes through the focal point. So to look at the image, we need just two if we draw correctly. Sometimes we may not be able to draw all three, but for most cases, we should be able to draw these threes. And we want to keep this in mind. The parallel passes through the focal point, just like for the mirror. But for the mirror, it went reflected and went through the same side of the focal point. But for the lens, especially this converging lens, is passing through the focal point on the other side. So here, this being symmetric lens, okay, so that's what I am talking about. Focal point are at exactly same distance on the both side. So that is red. Another one easier to draw and always possible is one that passes through the center. And the one that passes through the center is kind of entering by making 0-degree incidence angle or making 90-degree to the plane. So because of that, what happens? It goes undeviated. It does not bend. It does not refract. So now, when we draw them carefully with the scale, what happens is they meet over there. So that way we know this tip of this object going to be over here, and then the base always going to be on that optical axis. So that is the advantage of drawing this optical or parallel, principal axis. And this and that, they kind of look like reverse. So for example, if we were to go this way, so that's going to go passes through the focus. When it crosses the lens, then goes parallel, right? So we can think of something like that. So that's what's happening here. On this side, it's passing through the focus, hits the lens, and then now goes parallel. And it meets at that point as expected. Okay. So I drew these on a scale. So because of that, we can tell, okay, where the image is going to be. So for example, if you are drawing on paper, you can draw lens something like this and draw optical axis like this, and then make sure you mark both sides of the focal point at equal distance, okay? So maybe use a ruler and mark those points. So label them as a F just like I have done here. And then now you can start putting object anywhere you like and follow these rule and draw a straight line using ruler scale. And then what happens? You will be able to look at the image even without using the formula. And to see if it makes sense what you drew, if you want to check and you want to check that, uh, and you can do that by using this lens formula we used last slide. Okay, so here this is object distance. We are denoting object distance by P and image distance by Q. So some may denote this by DO. So I don't usually like to write subscript whenever I don't have to. So that's why I'm not writing one with the subscript here. And this is frequent, like let's say a practice. Many people and textbook uses P for the object distance and Q for the image distance, and that's what I'm using here. Okay, so with that, looks like it is 3:01, so good time to take break. So when we come back from the break, I'm gonna poll on this one, but just in case if you still want to look at it here, I'll just leave it here in the slide, and I'll see you in 5 minutes. Okay, welcome back, folks. So here is a question, and I'm opening the poll, and you have a minute to answer this question. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, so mostly D, that is correct. And here is another question. So the ray we are talking about is red. So I'm opening the poll. And again, you have a minute. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. So let's see what we got here. Oh, we got all of them. Bit more for D, and there are quite a few C as well. So D is correct answer in this case. The ray that goes parallel goes through the focus on the other side. Okay, so this is parallel to the axis. So when it refracts, goes like that. Okay. So now there is another question, and you have a minute.
No. Okay.
30 more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. So a bit more for C, and there are quite a few B as well. So it's like the opposite of what we had before. This now going to the focus means it goes parallel to the axis. Okay, so these things we need to remember. So that's why I am asking this, showing, telling, and asking you same question over and over again. So that's C, yes. So that way, once you know that, now let's see if we have something like this. Oh, let's make lens over here, like that. And of course, my drawing is not symmetric, but I'm assuming it's symmetric. So this is center of the mirror. So let's say if focus is here and focus is here, and if object is over there, a bit away from the focus, where the image is gonna be. Can you draw that? Can you practice that on your paper or tablet, whatever you have nearby? Can you look at the image of this by drawing 3 rays? One parallel, another to the center, another passes through the focal point. So do you think you can obtain image by, let's say drawing on the other side? So just like we had over here one passing through the focal that went parallel, right? So here that ray is this one that's passing through the focal point. Once it hits, it goes parallel. So can you draw other two? So I am drawing possible places for the image here. Let's say that is A, and this is B, and let's say this is C. So B is very close to this focal point on the other side. C is a little bit farther, okay? My best guess. So depending on these A, B, C, oh, I think I can draw another one here, D. So which one do you think is the position of the image? Close, of course, okay? So did you get the question? Okay, where would the image be? In this case? So now I'm opening the poll.
Is it okay if you repeat the question one more time?
Yeah, so there is an object. So now I have drawn these 4 lines. Out of 4, which is the most close to where you would get the image? Okay, which one represents the image, let's say? 30 more seconds. Five more seconds. Five, four, three, two, one, and it stops. Okay, let's see what we got here. So mostly we are getting B, but there are C, D, and A as well. So definitely not D. Definitely not A. So possible answers are either B or C. And B or C gonna depend on how close this is to the focal point. Okay, so let's draw. So that this line that is parallel that goes through the focal point, and we have to draw a straight line like that. Oh, looks like it's more like a C than the B. Hey, that looks like a C to me, but B was also kind of close. Okay, so that's how we should be able to locate the image. So here is another diagram here, a little bit just like we had in this question. See, the line was passing through this. So this happens when object is in between the focus or focal point and the lens. Okay, so in that case, so for example, when object is here, and then we have to draw one line going something like that, another line going something like that, another line going something like that. Okay, so that's what I'm showing you here. So in this case, object is within the focus. Okay, within focus, does not matter where it is. Okay, kinda is the nature gonna be similar. The ray diagram gonna look slightly different, but overall gonna be same. So in this case, it starts from the focal point and passes through that, right? So this ray of light. So we do not want to draw this way because that ray of light is not going towards the lens. So that's why we do not want to draw that. Rather, we want to draw this one here. And the one that goes parallel, of course, passes through the focal point, right? It can go like that. And the one that goes through the center goes on deviated straight. So now these are three. So they are not meeting here. Okay, they don't meet. So that means no real image. So what that means, just like you saw on the video, if you were to put a screen on this side for this situation, you wouldn't see the image on the screen. If you were to put a screen somewhere here, there wouldn't be any image. Rather, if you put screen over there, no, there won't be image either. Okay, but if you look from this side, okay, if you look from this side through the lens, then you will see, oh, there is image over there, and that image is pointing in the same side. Notice before when we are drawing this, the object was pointing up and image was pointing down. So this is inverted image where all the rays of light were meeting at that point. So that's why this is real, and real images are inverted. So over here, what do you see? Oh, Did I go? See, this is also real. That was inverted. Okay. I went backward, looks like. Yeah, this is where we were. In this case, they are not meeting. Then what do? We back produce them. So this dash line are the, just if you drew this with the scale, now you put the same scale along this line and then draw a straight line like that. Okay. And do that for this line as well. And do that for this third one as well. And if you drew them nicely with the scales with exact distance of these focal points, then they're going to meet at one point just like you see, and they are meeting here that I have drawn. Okay, so they meet here, and now this, since the rays of light, they don't meet but they appears when you look from here, right? So if you look from here, they kind of appears to be coming from that point. So that's where the image of this tip is. And for each of those points, you can draw several of those and then you get this image, but we don't have to. Just if we look at, an object is sitting on the axis, and if we look at the tip, then we know the base is going to be at the axis as well. So you can draw line to represent that image. Okay. So in this case, what happens? Image is large but not real because you cannot cast that on the screen. Another way to say that is they are not formed by actually, ray. They are not meeting at a point to form it, but they appears to meet at that point. Okay. So that's the main difference between real and uh, this is called virtual image. Okay, this is called virtual image. So virtual image are pointing in the same direction the objects are, and in this case this image is way larger than the object is, and we call this is magnified virtual image, upright, magnified, and virtual image. Okay, so now let's do a little bit in terms of number. So here from this to this is object distance, and this is focal point. From here to here is focal point, right? So now when object is within the focal point, that means it is somewhere between this point and that point, could be anywhere. So it looks like it is here. Let's say this is 3/4 way to the focal length. So P is that much. Okay. So for example, if focal length was 12 centimeter, then the object distance would be what? 3/4 of 12 is that 8? Right? 9. 9. That is 9 centimeter. This would be 9. So the number could be any. So I'm gonna, and I have done several of these in the note as well. And of course, all these diagrams are from the note. I spent, quite a few time drawing them. So now what we can do is we can use the mirror formula, for example, in this case. So 1 over, so let's say where the image is. Over here, we are showing it is far from the focal point on this side, right? So if I were to solve this equation, let's say what would I get? 1 over P plus 1 over Q is 1 over F, that is mirror formula. So P in this case is 3F over 4. So 1 over 3F over 4. And then there is 1 over F. Oh, maybe I should move this to the other side. Let's keep 1 over Q over here. And there is 1 over F. And then this when 1 over p goes to this side becomes negative, and that means we have 1 over 3f over 4, 3f over 4. So fraction of fraction, we can just flip it. So that's the, advantage of writing 3f over 4 rather than writing 0.75 of f. So now when we do this, what do we get? So 3 over 3f minus 4 over 3f. So that makes 1 over 3f, negative 1 over 3f. So q is negative 3f. So see here, this is f. So looks like this is 2 times f. I'm just eyeballing them. So looks like this is another f, and that is another f. So what this negative means? So when we have negative value, that means this is virtual, and that also means it is upright. So magnification is also 3 times here. So formula for the magnification is, let's say, negative q over p. So in this case, what happens? There is negative sign in the formula and negative sign in the q, and then p was, how much was p? 3 p is, yes, 3f over 4, 3f, oh, 3f over 4 means times 4 over there, right? So 3f cancels. So we have negative times negative, positive 4. So what it means is this size of this object image is about 4 times the size of this one. That's what it means. Yeah, my drawing, not this new drawing here, not that, but not accurate. But you see this 1 times, 2 times, 3 times, 4 times. So that's what the magnification means. So this time magnification positive. So when the image is pointing in the same direction as object, magnification becomes positive. Another way to say that is that when image is virtual, you get positive magnification. But when image is real, you have negative magnification. Okay, so that's how it works, folks. So this is for the, converging or convex lens. Now the idea is same for the diverging or concave lens as well. But there is subtle difference, so I like to point that out. So let's draw, oh, it's not exactly at the middle. So this is the axis, and let's put the, you know, yeah, I should be putting uppercase F for these, and lowercase f should be the distance. Okay, that's how the notation should be. My bad. And let's say object is, away from the one of the focal point on one side. Okay, so now let's draw. So let me clean these. Now let's draw 3 rays. Same 3 rays. Starts from the tip and goes parallel to this axis. Okay. So when it does, what happens is that, so this being diverging, the ray does not go like that. That would be the case for converging or convex lens, but that's not the case. So now it's diverging. So it's moving away. So in that case, so moving away from the base, I should say. So in that case, how do I know exactly whether it's going that way, or that way? So I drew that way. So it if we look from this side, it appears as if it is coming from this focal point on the same side, okay? So that's what guides us, which direction it should go. And then the one that is now heading towards the focus. Remember, for the converging lens we drew that passes from here, but we're not doing that for this. Rather, we are aiming for, see, this side we already used it. Now we want to make use of this side. So this was, let's say, heading to the focal point on this side. Now, after refraction, what happens? It goes parallel to this. Okay. Again, the idea is still same. So if I back produce that, then these two gonna meet there. So that means tip of the image must be here. So that means image is gonna be there. Okay. So this image is upright, just like this. And since the ray of light are not exactly meeting there, see, they are diverging here. So that's the name diverging lens. So they diverge. So because of that, what happens is we have to back produce them. And when we look from this side here, the rays of light appears to be coming from this point here. So that's why we say, okay, that's where the tip of the image is. We can also draw one more that goes, you know, from the center of the mirror. Okay. So it should go from there if I drew it correctly. So that's where the image is. So for this lens, no matter where they are, as long as it is away from this, the image is always going to be in between lens and the focal point. Don't believe me? Rather, you try drawing it by drawing at different places and see what happens. So size of the image is going to be different, but all of them are going to be somewhere between here and center of the, in between the lens and the focal point of that lens on the same side where the object is. So that's how it works, folks, for this one. So this is now image distance. No, this is object distance, right? So this was our object. This is our object distance. So that means this is going to be our image distance. Okay. So focal point we already showed. So that's that. Okay. So this image is virtual. So this lens always makes a virtual image, upright image. Okay. So here is, so while using this formula, we need to make sure that we are using correct sign. So I made this table and put it here. In my note, it is a bit longer version there, but that whole long version did not make sense to write here on the slide. So that's why I made it a bit shorter, compact form here in the table form. So in the formula, we have object distance, image distance, focal length, and the magnification. So these gonna have either positive sign or a negative sign. So when is it positive? Okay, when is it positive? So object distance is positive when object is real, but negative when it is virtual. So you may be thinking, okay, what is virtual object? Oh, virtual image we drew, but what is virtual object? So usually virtual object happens when we have combination of two lenses and mirrors and so on. So we'll talk about that one in the next chapter when we talk about optical instrument. Okay. So there is possible virtual object. So when object is virtual, its object distance gonna be negative in that case, and so on. Okay. So for upright image, we saw that in the slide here. Where was that? In this slide, image upright, and we calculated magnification as positive. Okay, so that's what saying in this table. Ooh. Upright image gonna have positive magnification, or if you get positive magnification after calculation, and then that means this is upright image. Okay, and if it is inverted, that means it has a negative sign, means it is inverted image, and vice versa. Okay, so that's how all of them are listed right here. And the slide is already posted on Canvas, so you should be able to figure that out. So to use this correctly, you have to use these signs correctly, otherwise this is not going to work. Okay, so keep that in mind. So this is the formula for magnification, image height divided by object height. But if we don't know that, then we can use image distance over object distance. So that means it is Q over P. So that's how it works. So this formula gonna work correctly and give you correct result only if you use these signs correctly. If not, then you may not get good result. And if you think ChatGPT gonna rescue you, most likely not. Okay. Even our notebook LM, it does not, always give you the correct result because it makes mistake while doing the sign convention. So best way to learn right here. So here is this question, okay? It says a small object is placed 24 centimeter in front of concave lens. So is it real object or virtual object? So this is real object. See, this says object is placed there. So if you can touch that object, you can place that object, that means it is real object. So that means object distance is positive 24 centimeters. And it says concave lens with focal length 12 centimeter. So since this is concave lens, so if we go back to that table, what do you see? Concave lens. Oops, what is concave lens? Concave means diverging lens. Another name for concave is diverging. So focal length for diverging is negative. Okay, so that's how you want to use that table. So Q is negative 24 centimeter. Real positive, virtual negative. That's easy to remember. Oh, it's not 24, it is 12. And this is not Q, this is focal length. Okay, what am I thinking? Looks like I need a break. Good thing we have a spring break coming next week, right, folks? So your assignment most likely gonna be up next week sometimes because they are not ready. Uh, I haven't, I'm working on. So I had these materials up to last week or so, most of these materials. So I was able to keep up with the time and pace of the class. But now I don't have new materials. So I have to generate them, and especially drawing the images and so on takes a lot of time. So I'll try my best, soonest, to put that there. So weekly most likely going to be up by tomorrow, but your pre-class assignment going to be up sometimes next week and not going to be due until the week we come back after the spring break. Okay. So before I forget, have nice break, and we're not done yet. Okay. Just wanted to give myself a little break and yourself as well. Okay, so that's that. Find the position of the image formed by the lens. So image position means Q is what? Okay. And it also says, is the image real or virtual? So if we get Q positive, that means it's a real image. If we get Q negative, that means it's a virtual image, okay? So that's how we can answer this question just by solving for Q. So 1 over Q plus 1 over P is 1 over F, and you know we can write this in any order we like, but of course we cannot put that in there. Q and P has to be on same side and F has to be on the other side. Okay, so 1 over Q is 1 over F minus 1 over P. So now should I plug in numbers, or maybe let's simplify this a little bit using our knowledge of algebra. Okay, and if going from here to here is too much for you, feel free to plug in numbers. Okay, so now that's 1 over Q, so Q gonna be Fp over P minus F. So now we have to be careful. Hey, it acts like a convex mirror. Concave lens and convex mirror, they kind of act similarly. And concave mirror and convex lens, both of them are converging, right? Convex lens, concave mirror, converging, and the convex mirror and concave lens, they are diverging. And that you can tell by just looking at the shape of the mirror and the lens. Okay. So anyway, so now let's plug in numbers with this sign correctly. So there is, this is product of F and P. P is positive, but F is negative. So there's going to be negative sign over there. So 12 times 24. And then now P is positive, but F is negative, and there is negative sign as well. So this negative times negative becomes positive. So that means it's 24 plus 12. Okay. Not 24 minus 12, but plus 12. So overall we get negative. Okay. So 12 times 24, and 24 plus 12 is 36, I think. 12 times 3 is 36. 3 times 8 is 24. So it looks like this answer going to be negative 8 centimeter, which is within the focal length, and that makes sense. Okay. So here definitely I did not make mistake. I can tell because this is less than 12 centimeter. And negative means it is virtual. How about we calculate magnification? Let's say magnification is negative Q over P. So Q is negative 8. So negative times negative is positive. So positive 8 divided by P is, object distance was 24. So that is positive 1/3. Okay. So image size is 1/3 of object. So it is small. So diminished, they call it. So that's how we use this formula with signs correctly. Okay. So now let's talk about, why we get this. So I briefly talked about this because the refractive index for different color is different. That's what I said. But let's write this down. So refractive index is speed of light in a vacuum over speed of light in a medium. And speed is written as a product of frequency and wavelength. So in this case, I'm writing frequency times wavelength in air. It should be vacuum, but air also acts like a vacuum for the light. Okay, so we can say that. And here I'm writing frequency same because frequency of the light does not change when it goes from one medium to another medium. So that means this is going to be same and it's going to cancel. That means I can write something like this. So now the wavelength in the air is longer and wavelength in the glass is shorter. And this wavelength in the glass for different light color is different. So different light color means different wavelength. Okay. So since each of the color has different wavelength and white light contains all 7 colors, what happens? Now when it passes through that, the refractive index being different for different color, they bend by different angle, slightly different angle. So that means they are spreading themselves. We call that dispersion. Okay. So now what happens is light ray bends with the least amount of the angle, and the blue disperses with the large angle with the normal over here. You see, if you do that, so red is just making this one. So red has the longest wavelength and blue has the shortest. Okay, so it deviates most. So because of that, what happens is the in the atmosphere acts like a, some sort of medium little bit. I know I said air doesn't have that much high refractive index, but air plus moisture and so on makes relatively a larger refractive index than just the pure air. And because of that, what happens is uh, the light disperses and red light mostly comes towards the, us, and blue light kind of skips over, so it scatters more. So that's why the sky looks blue. But once we out of the atmosphere, the sky is dark. It's not blue anymore. The sky is blue because of the atmosphere. Okay, folks? So now, before we go, here is one question. Looks like we have a minute, so let's go ahead and get it done. Oh, 30 more seconds. Yeah, I'm gonna close in 5 seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. So mostly B. We got quite a few A as well. See, the speed depends on frequency and wavelength. Since the wavelength is different for different color, speed gonna be different. So that's why A is not correct. Rather, B is correct answer. Okay, folks, so have a nice break. I'll see you a week after.